Reactions happen at different speeds. This can be observed in the world around us. For example, the metal on a bike rusting is a very slow process, and the explosion of a firework happens extremely quickly. It's important to make the distinction between chemical reactions and physical changes. A chemical reaction will produce a new substance, whereas a physical change is just where the appearance of a substance changes. An example of a chemical change is the burning of hydrogen to produce water, whereas the melting of ice is a physical change, as solid H2O has just become liquid H2O. A general rule to keep in mind is that chemical changes are difficult to reverse and physical changes can be reversed fairly easily. This lesson will cover the factors affecting rate of reaction and how to measure and calculate the rate of reaction. Particles must collide for a successful reaction to occur, but not all collisions are successful. There are a couple of conditions for successful collisions. The particles must collide with sufficient energy and with the correct orientation. Orientation is the direction of the particles, or which way up they are. For example, the reaction between the diatomic molecules of hydrogen and iodine. The two species must collide in the right direction. The first orientation yields no products because the reaction can't take place, but the second orientation does allow it, so two molecules of hydrogen iodide are produced. There are a number of factors that will affect the rate of a chemical reaction, and these can be manipulated to alter the rate. Concentration refers to the number of particles in a given volume. For example, a given volume of 2 mol per litre hydrochloric acid is going to have more particles in it than a given volume of 1 mol per litre hydrochloric acid. When there are more particles, there are going to be more collisions, and therefore more successful collisions. So increasing concentration of a reactant increases the rate of a reaction. Temperature affects the energy of particles in a reaction. So if particles have more energy, they're going to be moving faster and colliding more frequently. Since increasing temperature increases the energy of the particles, increasing temperature increases the rate of a reaction. When there is a larger surface area for reactions to take place on, rate increases. Surface area is increased by decreasing particle size, like how turning a solid brick of calcium carbonate into powder would be decreasing the particle size. There will now be a greater available surface area for collisions to take place on, so decreasing particle size or increasing surface area increases rate, and we'll talk about catalysts next. The defining features of a catalyst are that they are substances that can speed up chemical reactions, they remain unchanged by a reaction and then can be recovered afterwards, and they aren't classified as products or reactants, so they aren't found in word equations for a reaction. And there are some common examples like platinum, palladium, or rhodium, which are found in catalytic converters in cars to reduce toxic fumes produced from the exhaust, and iron in the Haber process, which is used to make ammonia. The rate of reaction can be monitored by observing changes in the mass, volume, or concentration of reactants or products. If a reaction produces gas, you can measure the volume of gas produced via displacement of water or gas syringe. With displacement of water, as the gas is produced, it fills the upside-down measuring cylinder and forces the water out. With the second method, the syringe expands as it fills with the gas that is produced. The gas syringe is the better option when a water-soluble gas is being produced, as the product will not be lost in the water. Measuring the change of mass of a reactant can be a useful method when gas is produced, as the purpose here is also to determine how much gas product is produced via the change in mass of the reactants. The cotton wool plug is important to allow gas to escape. This should not be drawn as a stopper, as that would prevent gas escaping. Gases that are less dense than air can be measured using upward displacement of air, because the gas produced is lighter than air, so it will move upwards for collection. This has a similar principle to the displacement of water, as the gas product pushes air out of the collection tube. For gases that are denser than air, downward displacement of air can be used, as the gas product will travel downwards. It's important to draw stopper lines that are not over tubes and scales on measuring cylinders and the syringe. The rate of a reaction as it progresses can be visualized as a graph. Here it is important to know the quantity of product produced or reactant used, as these values go on the y-axis with the corresponding time on the x-axis. Reaction rate decreases as it progresses, which is seen by the gradient or steepness in the line at points 1 and 2. At 1, the line is steeper, so the reaction has a greater rate than at 2 when the line is less steep. The rate is greater at the beginning of a reaction because the largest quantity of reactants is present at the start. As the reaction progresses, the reactants are used up and the rate decreases until the end point where the reactants have been completely used up. At the end point, the line becomes horizontal. This indicates that no more products are being produced. This shows a reaction between zinc and hydrochloric acid, which produces hydrogen gas, so the volume of gas produced has been measured. As you can see, when the reactant concentration is higher, this is the pink line, the reaction is proceeding faster due to the steeper line, and then it reaches the endpoint faster because the line becomes horizontal before the blue line becomes horizontal. And below the blue line is when the reaction has been carried out at a lower temperature. The line is less steep, so the reaction proceeds slower and the endpoint is reached later. As you can see, the yellow line doesn't even become fully horizontal in this given time period. The experiment results can be used to determine the average rate of the reaction using this formula, and this is how it will appear. These triangles here are said delta, and they mean change in. So this equation is average rate equals change in quantity over change in time, because this small t stands for time. The units for the average rate depend on the units used for quantity and time, so some common ones are shown here. For example, if you have quantity measured in centimeters cubed and time measured in seconds, when you put these values into the equation, you get centimeters cubed over seconds, which can also be written as centimeters cubed per second. When carrying out these calculations, you can read the quantity and time values from a table of results or from a graph like the ones we looked at earlier. In this example, we'll do the calculation from the values in this table of made-up experiment results. So the question asks, calculate the average rate of reaction between 20 and 30 seconds and give the correct units. So we're going to put in our formula and put in our quantity and time values at 20 and 30 seconds. So the quantity at 30 seconds is 25, and we're going to minus 20 because that's the quantity at 20 seconds. That gives us an average rate of 0.5, but we need to determine the units also. So using the units in the question, it's going to be centimeters cubed over seconds, which gives us centimeters cubed per second. So the answer is 0.5 centimeters cubed per second. That's all the new information for this lesson. On the next slide, there are a couple of questions, and there are answers on the following slide.